Hi, my name is Thomas and I'm applying as an aerospace engineer for Supersonic. And one difficult problem that I would like to share today with you is in regards to my soap film project with my second internship rotation at GE Aerospace. The tool I was developing, called soap film, was designed to generate minimal surface throat areas of nozzle passages, including dimensions, location, and STL mesh of the throat sheet. The issue with the tool after we created it was that the natural next step, once we had all the dimensions, locations, and mesh of the throat sheet, was why are two passages different? We know that they are different because of the dimension analysis. We know that they're in different places. We can see some visual differences if their large differences exist, but why is that occurring between two different passages that are supposed to be functionally identical? And the issue is that because the geometry is highly complex and three-dimensional in nature, simply looking at the two throat areas and trying to visually identify differences when the areas are only a few percentages apart was nearly impossible, very highly engineer dependent. So to solve this issue, I first tried developing a tool to centralize the meshes and use PCA, principal component analysis, to find the axis of most variation and then align it with the z-axis, and then do a similar process with the secondary variation axis to align it with the y-axis, which made all the meshes line up in the same plane. This is the throat sheet meshes of the passages. And that was decently successful, but it was still not to the level where we could really compare them together. And again, it's still just visual inspection. So the breakthrough technique was to move them slightly further away from the ZY plane, project them onto that plane, and determine what percent of the surface area of that mesh was aligned with the nominal mesh. And then the mesh is jiggled a little in all directions, and the scoring used to determine the proper direction of rotation and continue moving the mesh, iterating this process over and over until maximum alignment possible was achieved. And then, since all the objects are non-linear, they're axial, the nominal mesh was used to create curving interval lines, which are then superimposed all over all the other now aligned mesh scans. And the length of the interval line was then overlapped with that particular mesh, and those lines were measured, the overlapping portion on the mesh. And using that, I was able to create a graph of the width of each passage and use some light data analysis to determine the specific features of the passages which were non-conforming, so we could move forward in the most efficient manner possible to correct the issue. I'm quite proud of this project, as it's something that GE Aerospace has never done before, and it came purely out of a single meeting in which an engineer mused that it might be really nice to create some standardized method in which we could compare these meshes rather than the standard method of just having an engineer looking at them and making some informed decisions based on the visualization of the meshes. And doing this, we've been able to now identify several specific features of the nozzles that are causing these non-conformance issues, which it makes it, as I said, a lot more efficient in moving forward and redesigning and creating new drawings and manufacturing of these processes. Thank you for considering my application to Supersonic, and I look forward to hearing back from you.